Okay, let's see. Well, hello everyone. Thank you very much for joining us. I'm Daniela and I'll be your host. It is a pleasure to have with us Danielle Leonard from Newcastle University. Danielle holds a PhD from University of Oxford and then obtained a postdoc position in Carnegie Mellon University. She is actually a lecturer in Newcastle University, and her research involves testing and constraining extensions to the standard cosmological model, and with gravitational lensing and galaxy clustering, including improved methods for modeling, mitigating, and exploiting astrophysical modeling uncertainties, such as intrinsic alignments of galaxies. She is also a member of the LSST Dark Energy Science Collaboration, and today is presenting measuring intrinsic galaxy alignments for weak lensing. So thank you, Danielle. Please go ahead.
Okay, thank you very much, Daniela, and thank you for inviting me. Thanks everyone for coming. I can see, like you said, we have an audience across a number of institutions and maybe continents, so that's exciting. So I'm going to be speaking today about how we can measure intrinsic alignments to mitigate their effect on cosmological constraints from weak lensing. And so what I'm going to do is first I'll give a background. So I was told that we have a relatively broad astrophysics audience for this seminar. So for some of you, this will be very old hat, and for some it will hopefully be helpful in understanding the rest of the talk. So I'll give a bit of background about weak gravitational lensing, and then also intrinsic alignments and how they affect weak gravitational lensing measurements. And so going on from that, I'll talk about two different ways that we can try to, in some sense, directly measure the intrinsic alignment contribution to the galaxy lensing signal. So that's a particular type of a weak lensing signal that I'll introduce in the first section, and I'll present preliminary results from two students who I'm working with applying these two different methods, and then of course wrap up at the end. So to start with the outline. So the first thing I want to do is make sure that everybody is on the same page about what I mean by gravitational lensing and weak lensing. So just in case we have any people who are totally from outside the field, or maybe earlier year students. So gravitational lensing is the effect where you have the trajectory of light from a distant object being altered as a result of the presence of mass along the line of sight. So in the case of what we're talking about here, it's going to be a galaxy, a distant galaxy, which we often call a source galaxy. So it's the source of the light. And that light is going to be lensed by foreground matter. And so it's acting similar to an optical lens, but through sort of general relativistic effects. And so that's gravitational lensing in general. And so what we see on the left here is the sort of prototypical image that you might think of if you're a little bit familiar with lensing. And this is where we have the very bright foreground object. I hope you can see my mouse. If not, well, you can probably pick out the bright foreground object. And you have around it these other galaxies that are in the background being preferentially oriented in our image tangentially to that bright object. And so that tangential shearing of the images around the bright object is an example of gravitational lensing. And in this case, it's of what we tend to classify as strong lensing, because we can actually look at this image and see, yes, there is a lensing event happening here. Weak gravitational lensing, which is the case that I'm talking about in this talk, is the other end of the spectrum. So it's the case where it's the limit where we can't just look at the image and see that there is lensing happening by picking out multiply imaged objects or arcs like we see here. Instead, we have to detect this effect statistically because it is present at a low level. But it turns out that detecting this effect statistically over large populations of galaxies can actually be very useful in learning about cosmology. So there's kind of two main ways that I'll focus on that we think about weak gravitational lensing and measuring it cosmologically. There are certainly other ways as well, but these are the kind of two, I'd say, sort of bread and butter ways. And so in general, to measure this weak lensing, as we can't detect it for individual objects, we're thinking about measuring correlations between pairs of galaxies. And so the way this works is that kind of illustrated on this graphic here. So here what we have is a bunch of galaxies in the background. Again, I hope you can see my mouse. And we have a sort of cluster of galaxies in the foreground represented as part of a cluster of dark matter as well. And so the galaxies in the background are, in reality, have a certain orientation, which is depicted on this the background panel here. And in the foreground, what has happened is that they have undergone lensing as a result of their light passing by the foreground objects and dark matter. And so what we see is that there are correlations that emerge between the shapes of the observed shapes of the background galaxies. So the two main ways that we see the background galaxy shapes changing is, or their background galaxies changing, is that lensing will cause their shears and their shapes to and their orientations to change, and we call that effect shear. And there's also an effect where lensing will cause their brightness to change. We call that magnification. But I'll be focusing on shear here because that is the way we tend to observe this effect. And so when we have light from these background galaxies passing through the foreground large-scale structure, what we find is that if we look at pairs of galaxies, for example, although you could do this with sets of three, and people do, but in the simplest case, if we look at pairs of galaxies and we look at their images, and we consider pairs that are close to each other angularly on this, what we can realize then is that the light from both of these galaxies is going to propagate through the same cosmic structure. And that's to a greater or lesser extent, depending on the redshifts of these galaxies, but you will see correlation between the shears that are induced by the foreground matter, because it is, in fact, the same foreground matter that the light is propagating through in both cases. And so if we were to look at the correlations between pairs of background galaxy shapes, we would call that cosmic shear, because its correlation is in pairs of and shear of pairs of galaxies, which is induced by the cosmic large-scale structure. So that's one example of a way that we can think about weak lensing. And then the other case is the case where you would look at correlations between the shear of one background galaxy and actually the position of a galaxy in the foreground. And the reason that you would expect a correlation there is that the galaxy in the foreground is tracing the matter distribution. And so the galaxy in the foreground is associated with the matter that is actually inducing the lensing. And so this is what we name galaxy-galaxy lensing. So I'll be speaking mostly about galaxy-galaxy lensing during this talk. Essentially, you can think about both of these as being 2-point correlation functions, and where the cosmic shear is a 2-point correlation function between the shapes of two background galaxies, or the shears of two background galaxies, and galaxy-galaxy lensing is a two-point correlation function between the shape of a background galaxy and the position of a foreground galaxy. And there's a couple of different ways we can sort of relay this two-point function for galaxy-galaxy lensing. One way we relay this information is through the statistic called gamma t, which is the tangential shear. So that is going to be a measure of, on average, how much are the images of the background galaxies stretched along the axis that is essentially a circle around an annulus around the foreground galaxy. So what is the enhanced tangential orientation of those galaxies? So similarly to how we had those rings in the strong lensing case, what is the degree of that effect? And in a very related quantity, we could also translate that to this quantity called delta sigma, which is the differential surface mass density around a lens galaxy. And when you think about it, it makes sense that because we know that it is a distribution of matter that's doing the lensing, we can basically measure tangential shear and translate that into a knowledge of what is the matter distribution around a foreground galaxy. So those are the two sort of statistics that we measure for galaxy-galaxy lensing in general. I want to just ask if there's any questions at this stage, especially if there are some people who are maybe in different areas of astrophysics, or, oh, sorry, I've gone ahead by mistake. I don't know how to go back. This is horrible news. Okay, there we go. Anybody
can I ask
yeah.
Can I ask a question here? Do you mean that you can, when you talk about the distribution of matter in the foreground, do you mean that, for example, you can probe the dark matter distribution in a halo, or nothing to do with that?
Yeah, no. So it's sort of yes. So it is a statistical quantity, so it's going to be like the it's not the particular differential surface mass density around a given lens, okay. But it's like stacked on the different lens galaxies. If that makes sense. Yeah.
Okay.
Yeah. Any other questions at this point? I can't see the hands, unfortunately. Or yeah, I can't see the hands. I just can't see the chat. Okay. All right. If not, I will carry on. Right. So now I've got. Hopefully you can't see. Okay, there we go. This is going so well. Okay, there we go. Great. We're back on the slide I meant to be on. So what I was going to say here is just that because we're measuring weak lensing statistics as statistical quantities, we're measuring them around for populations of galaxies rather than individually. Our statistical uncertainty is really dependent on the number of galaxies for cosmic shear in our source sample, and for galaxy-galaxy lensing it depends on our source sample as well as our foreground lens galaxy sample. And so this is just to illustrate sort of where we are and where we're going. So the two ways that we can sort of increase the number of galaxies in our source sample is more area and more depth. So the purple dots are sort of surveys that are with analysis that are ongoing. So we have HSC, KIDS, and DES. And we're kind of heading towards the top right-hand corner of this plot, which is where we have surveys like Euclid and LSST. And so we're kind of, and so Euclid is, in principle due to launch in the next couple of years, and LSST, we're hopefully going to start survey operations in 2023 after a delay from the pandemic. So we are sort of relatively quickly approaching a point where we're going to have a bit of a step function in terms of the statistical power of our surveys. And one thing that means is, of course, that we have to be more careful than we've ever had to be before about modeling other other effects that could contribute towards these signals that we're measuring. And so the one of those that I'm going to be speaking about today is the intrinsic alignment of galaxies. So when we measure, as I said, weak lensing, what we're really doing is measuring correlations in the shapes or in the measured shears of pairs of galaxies, usually pairs. And so we, the large part of that signal is going to be due to lensing. But there are reasons that you could have correlations in the shapes of galaxies other than lensing. And so this is kind of what we're looking at here. And so one of those reasons is tidal effects, essentially. And so here we have an illustration of the ways this could come up for cosmic shear. So we have two sort of sets of images. We have this set of 3 on the left here, and we have this set of 2 on the right. So on the right in the upper corner, if we imagine that we are sort of here looking out into higher redshifts as we go up this way, we have what we're seeing in this bottom square, and we have 2 galaxies that are in our source sample, which are both intrinsically tidally stretched by a dark matter halo that we can't see. And so because we have, many hundreds of thousands and going towards LSST and Euclid millions of galaxies in our source sample, it's not like we're going to be able to pick this situation out by hand. And what happens is we have effectively these tidal stretchings are acting in the opposite way as what a shear would do if, for example, you had this dark matter halo being at a lower redshift. And so you have a reduction in your overall weak lensing signal as a result of this type of intrinsic alignment. You could also, in the case of cosmic shear, where you're measuring correlations between two shapes. You could also have the case where you have a background source galaxy, which is being sheared by an intervening dark matter halo, but you also have another source galaxy at the same redshift as that dark matter halo. And what you end up with is one galaxy that's tangentially sheared and another galaxy that is radially aligned. And this is another term which also decreases your signal in your weak lensing cosmic shear correlation functions. And as I said today, I'm not focusing on cosmic shear. I'm actually focusing on the other type of lensing, which is galaxy-galaxy lensing. So in that case, what we actually have is slightly different. So because we are now correlating positions rather than positions with shapes rather than just shapes, what we have is the case where we have a lens galaxy, which I've very artfully represented by this black circle. And we have a source galaxy, which is this blue one here, which we have in our source sample. So what happens is you end up with this galaxy, this blue galaxy, being radially aligned, right? And so you might be thinking, okay, but like, why don't I just not have that galaxy in my source sample? Because if I knew its redshift, I can just cut it, because this will only happen when this galaxy in the source sample is actually physically close to the galaxy in the lens sample. So why don't I just make a cut on redshifts so that there's enough separation between the lens galaxies and the source galaxies that doesn't occur? And the answer is that would be very nice if we had spectroscopic redshifts for all our source galaxies, which we absolutely do not, due to the numbers of source galaxies which are involved in these measurements. Like I said, you're talking about hundreds of thousands to millions. I'm sorry, that's orders of magnitude lower than what I'm meaning to say. We're talking about hundreds of millions in some cases. And so we just don't have spectroscopic redshifts for all of these. And so no matter how good our photometric redshifts are, we are, it's not going to be perfect. And so you are going to have some small fraction of your source sample, which actually is physically close to some of your lens galaxies. And so you are going to have an intrinsic alignment contamination at some level. And so this is why it's kind of important for us to be able to model this signal in the case of galaxy-galaxy lensing as well. And of course, learning about how this alignment manifests in the case of galaxy-galaxy lensing, it's also useful in terms of understanding it for cosmic shear, where you can't actually make that redshift cut, even if you did have spectroscopic redshifts. Where am I going now? Yes, okay. So, right. So, oh yeah, sorry. I was just trying to remember what I was going to say. Sorry. So I was saying like this is due to tidal physics, right? And you might be thinking, well, I'm actually just going to go back here because it's probably more relevant. Here, you might be thinking, well, like we kind of understand how tidal physics works. So like why are we worried about this? We can just model it and we'll be able to subtract it off. And to some extent that is true at larger scales. So we have a pretty good idea that tidal physics dominate this effect at larger separations between pairs of galaxies. It's still not the case that we understand perfectly what the sort of amplitude of the effect is, because you do still have, galaxy level like astrophysics that is affecting like how much does the galaxy actually get stretched, and at which does the if it's not very much, then you also have to account for the torquing and how much is that affecting things. But that, it's basically we do sort of understand at larger scales up to a factor of a constant what's going on. At smaller scales, it's much more complicated, and there are also effects like galaxy formation history and galaxy evolution, which and environment, which we haven't yet established good modeling for in terms of understanding how intrinsic alignments work at those smaller separations. And so that's an area where we can make a lot of improvements and hopefully improve our modeling such that those sort of intermediate and smaller scales can be more reliably used in our cosmological analyses. Of course, there's other issues with using those scales in our cosmological analyses, like baryonic physics, et cetera, but we're working on all of these things simultaneously. And so, right, so how could you think about measuring intrinsic alignments in order to, help us with model building and testing? So there's a few ways I can think about to do it. So the first one is that if you have a survey or if you have a set of galaxies, sample of galaxies, where you have spectroscopic redshifts and you have shear or shape estimates for your galaxies, great, you can measure this effect directly. So you can actually just go ahead and measure the correlation between it's basically the same correlation that we're talking about with galaxy-galaxy lensing, but you can just make a cut such that because you have spectroscopic redshifts, you can make a cut that's pretty good, such that you're only looking at lens and source pairs where you know that the redshifts are close by, and so that's pretty nice. And an example of that kind of work is here on the left from a paper by Sukdeep Singh a few years ago. And so you can see like this is a real effect, like we do see it. And by only looking at galaxies where we have a small redshift separation, there is effectively no lensing at that point. And so we are actually measuring this intrinsic alignment signal. The problem with this, sort of the con to this, is that you can only do this on galaxies where you have spectroscopic redshifts, because otherwise you can't make that cut reliably. And so what that means is that by definition of the fact that you have spectroscopic redshifts for your sample almost, you are going to be working with a different galaxy population than those which are truly in a source sample. So you're going to be working with brighter galaxies, for example, and which is going to have correlations with mass. and which we know does have correlations with the intrinsic alignment that we expect to see. So this is great for model building, but only with the caveat that it may not apply exactly to the galaxies that we are actually interested in applying to. So it's still an important part of our toolkit though. A second thing we could do where we would use the kind of correct galaxies is to constrain the parameters of an intrinsic alignment model indirectly as part of a cosmological analysis. And I can see that for some reason this isn't showing up exactly right, but you can kind of still get the idea on the right here. You can't see the labels, I'm sorry about that. But this is just some parameters that are of intrinsic alignment model TATT, which are being constrained for color separated galaxies as part of a parameter inference analysis, where basically you would measure the whole weak lensing, cosmic shear, galaxy lensing 2-point functions, and then model it as a combination of lensing and an intrinsic alignment model and constrain the parameters of that model. And of course, that has the benefit that you are actually using a appropriate source source sample, but it means that you're very model dependent. So you're doing it for a particular model, and you're doing it as part of a parameter inference pipeline. And so the third option is kind of the option that I'm going to talk about in more detail for the rest of the talk. Which is kind of what I'm calling like directly. So it's not direct in the same sense as option 1, but it is more direct than option 2. And in this case, what we're doing is we're combining measurements of lensing statistics in a way that allows us to hopefully null out the lensing signal, which should only leave the intrinsic alignment signal. And so then we get what is a model independent, in the sense of independent of an intrinsic alignment model, measurement of the intrinsic alignment signal for hopefully testing and building models of that signal. And so there's kind of a couple of different ways you could think about doing that. Probably more than a couple if we all put our heads together, but there's kind of 2 that I'm going to be talking about and 2 that are in the literature. So one way is that you can think about the fact that intrinsic alignments, like I just said, in the case of galaxy lensing, occur when you have galaxies in the lens and source samples which are close in redshift. So if you construct an estimator where you are subtracting a close redshift bin, a lensing measurement, a gamma T measurement or a delta sigma measurement from a close redshift bin to your lenses from one that is using a higher redshift bin, a further away source redshift bin from your lenses, the intrinsic alignment contamination of those 2 is going to be different. And if you can appropriately normalize them such that the lensing cancels, you can try to extract the intrinsic alignment signal. So that's one strategy I'll be talking about. Another strategy I'll be talking about has to do with the fact that when you use different shear estimators for different, which have different radial dependencies, you actually get a difference in your intrinsic alignment measurement. And so, but the lensing measurement stays the same. And so I'll talk about how you can try to exploit that as well. So yeah, so that's kind of the next 2 parts of the talk are talking about these 2 ideas of these methods and showing some results from them, preliminary results. So at this point, though, I just want to, obviously this has been a long background, but I think that's appropriate just in terms of introducing the topic. So I want to just pause for questions at this stage.
Just a small question regarding this discussion here about the noise. Would the 3-point function be less problematic with respect to this noise, or I mean, if you look at three galaxies instead of 2, or not?
You mean with respect to the noise? Sorry, I'm not sure exactly which part of
I mean,
the
of
noise
this
you're talking about.
galaxy, of this IA, like when you have some source galaxy near the same redshift,
Yeah.
and you align the thing.
Right.
So if you look, for example, at the 3-point function of 3 galaxies, if they are distributed, around around the halo, they would all point, say, towards the halo, right? While if the effect is due to some, other galaxy near the halo, then I guess, I mean, I'm probably saying something very silly, but it will help me just understand the picture.
No, I don't think you are. So yeah, I guess I haven't personally myself worked on 3-point estimators, but it's a good question. I'm trying, yeah, I think, because usually we would talk about 3-point estimators more in the sense of a spectroscopic survey. I'm not aware of, I think there might be issues with using 3-point functions for a survey where you're using photometric redshifts, because you'd end up with, like, it'd be like an angular 3-point function, which may or may not actually have very much information in it. Yeah, I'd have to think about it. Yeah. Sorry. Any more questions at this point? Okay, if not, I will carry on. Okay, so the first kind of idea that I'm going to discuss is this idea of using different redshift bins and combining them to try to get at the intrinsic alignment signal. So, like I just said, if you have, this is a schematic diagram. So if we imagine that the lens redshift distribution is centered at this purple line. So this is a redshift distribution plot. So on the y-axis, we have the number of galaxies in a given redshift bin, I guess, and on the x-axis we have redshift. And so if we imagine that we have a lens sample that's centered at this purple line, and we have a source redshift distribution that sort of cuts across it, as in this black curve. If we take bins of source galaxies A and B as separated by this dashed line, and with bin A also being bounded either at the purple line or a little bit further ahead, bin A we would expect to have a higher intrinsic alignment contamination to a galaxy lensing measurement, with the lenses being this purple line, compared to bin B, because we would expect that the photometric redshift uncertainty would cause more issues in terms of galaxies from bin A ending up actually being close to the lens galaxies rather than bin B, because there is just a greater separation. So remembering that this cut on these redshift bins is a photometric redshift cut. And so what a paper by Jonathan Blasek in 2012 proposed was using this idea to isolate the intrinsic alignment signal. And so this is a horrible slide, and I do apologize. But the general idea is that you take a 2-point function of galaxy lensing between the sample A and your lenses, your close by samples to your lenses, and you subtract a 2-point function with sample B and your lenses, and you divide out by the number of pairs which you believe to be subject to these intrinsic alignments, and you get your intrinsic alignment contribution to the signal per contributing pair. And so explicitly, this looks like this horrible thing with these arrows going everywhere, and I should have probably done a different method of indicating what these things are. But for those who would like to know, we have this delta sigma showing up for each of these samples, and we have we have a photometric bias term, photometric redshift bias term, and on the bottom here we have this thing called the boost factor, for each of these samples, which is essentially a correlation function in position between the lenses and sources. And we have the critical mass density of each sample, which is how we convert between delta sigma and gamma t. This is not super important other than to say that delta sigma, because we are measuring because it is a measurement of the sort of averaged mass around the lens galaxies, is in principle, if it is only lensing, should be the same for no matter what source sample you are using, because you've already sort of in constructing this delta sigma quantity, you've already converted from your sort of tangential shear measurement to the estimated stacked mass distribution via redshift related quantities. And so the idea here is that on top of this estimator, if you had nothing but lensing, and you were appropriately correcting for photometric bias, photometric redshift bias, you would have, this would be 0. And in fact, if it is not 0, then what you are left with is intrinsic alignment. So that's the idea. And so in that original paper, they were able to place some constraints on this intrinsic alignment quantity. I'm sorry about the resolution of this figure, where these black data points are the model independent measurements, and then they also show these confidence intervals for if you are looking at particular models. You can see here that this is a sort of null result, so it's not seeing an intrinsic alignment signal different from 0. And this is again back to 2012, so we're using SDSS galaxies. So what we've been doing recently is, because that paper was sort of a proof of concept using, at this point, a data set which is a number of years old. We've been doing with Sarah Safari, who's a student at EPFL, as well as Jonathan Blasek and myself, have been applying this estimator to data from Dark Energy Survey Year 1 public data, which with some slight tweaks in order to try to see if we could actually use this method to get a measurement rather than just a constraint. And there's a few tweaks that we've had to make here. So because we are working with photometric redshift for the lenses, although of course, I shouldn't say of course, although the Dark Energy Survey Red Magic lens catalog has pretty good photo Z, they are still photometric. And so we are then working in terms of angular scales rather than physical separations, because it's much more difficult to work in terms of physical separations when you don't have sort of extremely reliable redshifts for your lenses. And we are also using a version of the estimator which uses gamma t rather than delta sigma directly. But given all that, currently, I mean, Sarah is seeing some preliminary results that are quite odd, actually. So we're trying to understand them. So this is what Sarah is actually at the moment. So again, this is very preliminary, but you can notice that one of these data points is a different color than the rest. So in the convention that we're working in here, the intrinsic alignment signal is actually expected to be negative, because as I showed you earlier, the intrinsic alignment is sort of the opposite effect in terms of correlation to the lensing. So it's sort of anti-correlated, where we consider the lensing to be positive correlation. And so we would expect that the intrinsic alignment contamination to gamma t, were it present, would give a negative signal. And we have one negative data point here at the moment, And then all the rest of these are we're finding them to be positive. And so this is very much trying to understand what's going on here, stress testing. We have a, very preliminary suspicion that what we could be seeing is that we are actually seeing an intrinsic alignment signal at this very small separation. At larger separations, potentially what's happening is that there is a photometric redshift uncertainty that we're greater than what we were accounting for, and that could be sort of winning at those larger scales. This is still very much work in progress, but it's interesting to see that at least statistically, we appear to be in a regime where we should be able to actually measure something here, as opposed to the previous measurement from a number of years ago, which was just placing constraints. If it's still the case that we are trying to understand systematically what exactly is going on here. So the idea then, of course, would be that given that we understood our signal, we would then be able to compare it to what we do have in terms of modeling and place constraints on those model parameters, which could then be propagated into weak lensing analyses, specifically potentially for DES data, and also as priors on weak lensing analyses for other surveys. But of course, at the moment, this is a very preliminary, slightly confusing plot. So that's the case where we're using our multiple redshift bins in order to try to null out the lensing signal. And then in the last little bit, I'll talk about another idea, which is this idea of using multiple shear estimators. So what are we talking about here? So something that has been observed in simulations as well as in observations is that if you have, okay, so a galaxy shape, clearly it's not something that the galaxy like walks up and tells you what the shape or the shear is. Like, you got to measure it somehow, and there are different ways to do that. And essentially, you're talking about image analysis at the end of the day, and the different methods that you can use to measure the shear or the shape of that galaxy are going to be more or less sensitive to the inner or outer radial regions of the galaxy light profile. And so what's been found in these simulations, as well as in this observational work, is that when you use methods that have different radial sensitivity, your intrinsic alignment signal shifts by a constant. And just to motivate why the intrinsic alignment signal would shift, you can imagine from the tidal, the sort of tidal physics side, that the sort of outer regions of a galaxy would be more impacted by tidal stretching than, for example, the inner core regions of a galaxy. And so the alignment induced by that tidal field would be like physically greater if you're measuring an ellipticity as your probe of that, which is more sensitive to the very outer radial regions of the galaxy, versus if you're measuring an ellipticity, which is more sensitive to the brightest parts of the inner region of the light profile. And yeah, to reiterate, like, that is a physical effect, that the tidal stretching is having a greater impact on the outer parts of the galaxy. And so the idea is to take advantage of what we see, which is that these correlations are showing up at a different amplitude with the same scale dependence to try and actually constrain the scale dependence of this signal. And so this was something that I developed in a paper a couple of years ago, looking at an estimator which can take advantage of this and sort of seeing how we think it would work. Schematically, again, the general idea is you measure the shear using you measure your tangential shear using both your two estimators, and your intrinsic alignment is shifted by a constant. And so if you combine your two measurements, you get your intrinsic alignment back shifted by a constant. And so explicitly, again, see, this is a little bit better. This is what I was going for in the previous one, but clearly it's worked out better in this case. So explicitly, we have this same quantity gamma IA, so the intrinsic alignment contribution to galaxy-galaxy lensing. We're subtracting our two tangential shears from our two methods, and again, we have this boost factor. We also have this F quantity here, which has to do with the fact that effectively what we're doing on the denominator here is we're trying to account for the number of pairs that are contributing to intrinsic alignment again. And your boost -1 is giving you the number of pairs that are in excess to a random field because it's a clustering correlation function. And your F comes in and says, okay, well, but also there would be some galaxies that are in close proximity, even if we only had a random field of galaxies. So your F sort of picks up that little extra bit of galaxies that would be there, even if all we had was no gravitational clustering. But you can think about the denominator here again as just being the number of pairs of galaxies, which we expect to be subject to intrinsic alignments. So given this estimator, we hope we could constrain, if not the amplitude of the intrinsic alignment signal, because we do have this constant A, which we would have to be able to figure out how to put a constraint on it separately to be able to really extract gamma IA, we hopefully could extract the scale dependence. And you might be like, well, this seems like, categorically worse than the other method I talked about, right? Because the other one, you could get the actual amplitude. So why would you consider this method? And the key thing here is that this method, because it is less dependent on redshift-related quantities, is more robust to specific issues with the sort of redshift calibration that we expect to have with deeper surveys like LSST. So by redshift calibration, that's a bit of a bad word to use for it because that means a specific thing. But what I mean is, in, for example, the Blaythe 2012 method, we needed to have that photometric redshift bias parameter C. And in order to estimate that, you needed to have a representative subsample of your source galaxies with spectroscopic redshifts. With LSST, it's going to be very, very difficult to get a representative subsample of source galaxies with spectroscopic redshifts at the faint end. It's because they are just going to be so faint. We're going down to a magnitude limit of 27, right, in apparent magnitude. That's going to be very, very difficult. And so to have a method that is much less sensitive to that is sort of invaluable. And so, and when we did propose this, we did test and we did in fact see that it is much less sensitive to those kinds of systematic uncertainties with lack of spectroscopic subsamples. So so like I said in this original paper, we forecast the method performance, and this is what we see in contrast to the first method that I mentioned, so to the redshift Nulling method, and where we are probably running pretty close to time at the moment. So I'll try to wrap this up quickly, but so we see that we have this two-dimensional plane where we're looking at the ratio of signal to noise of this method to the Blaythe 20. So the black line is where they're the same, and we have this 2D plane. And what is this 2D plane? So we have this A, which is the constant, which is the difference between the intrinsic alignment amplitudes. So essentially that depends on the radial sensitivity, the difference in radial sensitivity between the two methods. and we have rho, which is the correlation in the shape noise between the two shear measurement methods. So to get sort of the best improvement in signals to noise, we want to have two shear measurement methods which are radially sensitive to different regions, but have highly correlated shape noise properties. Now, this is, of course, like I said, this is to improve the signal to noise. That's nice, but the kind of main selling point here, like we said, is you kind of need insensitivity to a lack of a spectroscopic subsample for these speed surveys. And so there's kind of those two things in conjunction. So this is what we think is going to happen. And of course, it's nice to see if what we think is going to happen is actually going to happen. So this is a project led by my master's student, Charlie McMahon. And what he's been doing has been playing with, again, Dark Energy Survey Year 1 catalogs to kind of do a proof of concept measurement. So DES released shape catalogs with two different shape catalogs with two different shear estimators, M3 shape as well as metacalibration. And so we have no reason to believe that those are in the sort of top right-hand corner, the sweet spot that in terms of their correlated noise and their radial dependence, but they are a data set that is available where we have two shape measurement methods and where we're interested in looking at intrinsic alignments. So what Charlie has been doing is basically applying this method using those catalogs and seeing if we can at least figure out where all the issues crop up when actually applying a new method to real data, which is always fun for the first time. And so he's been having a lot of fun, running into a lot of brick walls with different problems that turn up. And this is a very preliminary plot, which we are actually hoping these error bars are like vastly bigger than what he's actually going to end up with, but we'll see. Experimenter bias. I don't want to say I'm hoping for anything really, but he is essentially at the moment he's having some uncertainties on estimating his uncertainties. And so we figured for the preliminary plot, we'd show the one with the biggest uncertainties just to be safe. But there's been definitely some good lessons along the way about, for example, selection biases. So if you want to have these two shape measurement methods, what you need to do is create a matched catalog between two. If you have two catalogs with two shape measurement methods, you need a matched catalog to be able to actually get the same lensing signal and null it out properly. But when you have a matched catalog, you're imposing a pretty complicated selection function on your sample, and that's really non-trivial for example, for metacalibration and estimating a selection bias correction. And so there's kind of questions about like, if this is going to be useful, does it need to, this method, does it need to be like known in advance and like prepared for when we are figuring out what quantities need to be captured from for a given shear measurement method in future surveys. And like I said, this is very work in progress, so there's still some things we're very much checking. We are like basically out of time, but I will say just real briefly that something that I'd really like to work towards is figuring out how to get to the top right-hand corner here. So developing sort of either a pair of shear estimation methods that work really well together, or more likely working off something that we already are using and that we already hope to apply to something like LSST, like a metacalibration, and saying, okay, what is the optimal sort of pairing for metacalibration, so that we're working with as much of what we already have as possible. And I will, I think, just sort of stop there and conclude and say, I hope this has been like at least a little bit interesting in terms of thinking about, I'm aware this is a very specific systematic effect that probably a lot of you, like if you're not in weak lensing cosmology, maybe don't care that much about, but I hope, it's been maybe a fun opportunity to think about something different. And yeah, I hope this has been interesting. And in the little time we have left, I'm happy to take any more questions.
Mm-hmm. Yeah, Danielle, thank you very much. We have time for questions. So if you have any question, just unmute and ask. Well, I have a question, but it's a very general one. How these other surveys like in other wavelengths can help you in this work? For example, SKA or something.
Okay. Right. So that's an interesting question. So obviously SKA is in the radio. Weak lensing in the radio is like a whole thing. And I'm sure there might be someone on the call that has a lot more knowledge of it than me. Weak lensing in the radio, I think, is a very specific topic that people work on because radio is, you know, your images are like in Fourier space, right? So like the problem of measuring a shape in the radio is non-trivial. At the same time, we actually have like shape measurement methods that are potentially the ones that are going to be sort of the next generation. It's like, you know, it's like meta calibration, the next generation. So, which is actually called like Bayesian Fourier domain methods. So, which actually involve taking a Fourier transform of the image. And so I wonder if actually those could end up being applied more naturally in some sense to radio data. I think like also generally in a more basic way to answer, you can imagine that like if what you are doing is trying to do these like specifically if you're like working more on the direct method of measuring intrinsic alignments, you can imagine that like having different wavelengths helps you because, you know, if you are, especially if you're working just making direct measurements, like just having different tracers of the same galaxies, like you're going to potentially see things that you wouldn't see in the optical. And so maybe there are galaxies where like the bits that are actually being tidally stretched are actually like being picked up way better in the radio. So that, I mean, that's kind of spitballing, but I don't know if that's actually something that could work, but yeah.
Thank you. More questions?
I was just curious. I'm really excited about this multiple shear measurements method that you were discussing. If you could tell people what to do, more technically, which two types of, what should be run, on those thousands of degrees of data?
Yeah, so I mean, this is kind of the question. So like, that's kind of what I was alluding to at the end, that like, I think there needs to be, I want to do some like simulation work and like studies and just using things like, Galston and whatever to figure out like how to optimize like a radial weighting for, I mean, I think my initial thought would be to use, to use something like NGMix with Medi-Cal, and but use like a version of NGMix where you have like optimized, you have like flexible radial weightings, and so you can, because you really would need to like test the estimator to see like the estimator pairs to see like how is the shape noise responding, how is the like where do you lie in that 2D plane, and so I think it's like it's not well understood right now, like which what two things you want to use. Yeah, I'd love to talk more about this, Daniel. I think like the other thing is, like I said, like I think it's really hard to go back and do this like after the fact, but it might be much easier to do it like if we know it in advance of running a pipeline to like add a step, if that makes sense.
And, we're sort of in that place now with GSY6.
Y6, yeah, exactly.
So I don't know how flexible we are yet still at this point, but
yeah.
I would agree with you that you want to meta-calibrate, with the same random seed and all, and just two ways of measuring shape that are different that are sensitive to different scales. So that's
that would be ideal. Yeah.
Great, thanks.
Yeah.
One more question. Okay, if not, well, thank you very much, Daniel, for being here, accepting our invitation. And thank you everyone also for joining us. It was a very good talk, very clearly. Thank you very much.
Thank you very much for having me.
Yeah, have a good day.
Thanks a lot.
And good night.
Yeah.
Bye-bye.
Thanks.